Consider a concrete example of the class of problems that we have just studied, which is we're going to maximize a utility function over how much of good X and Y gets consumed. The level of consumption of both goods have to be non-negative. This is the budget constraint, so this is the price for good X, this is the price per unit of good Y, this is the total wealth. And A and B are positive constants that affect the weight of the preferences given to both items. Now, we're going to solve this problem in two steps. Step number one is going to involve asking if the solution is interior. Okay. And we're going to do that by taking advantage of the same logic that we developed before. So we're going to rewrite the problem as maximize over X greater or equal than 0, X less or equal to of W over P of A log of X plus B log of W minus PX divided by Q. And as before, we are going to define with a double minus sign this as a cost function, z of x. So it's exactly as before. Now, given that, now let's plot what the first order conditions of the problem look like. We're going to maximize over x. The feasible set is between x equals 0 and x equals w divided by p. We know that once x is determined, y is determined by this equation, given that comes from the quality constraint. And what do we know? We know that u prima is going to be a function that looks like alpha over x. And remember, by the interpretation, this is going to be the marginal benefit. So that's going to be a curve that basically starts at infinity and it goes down like this. This is u prima, which in our interpretation, again, is the marginal benefit. Now, what is the cost function going to look like? So the cost function, which is described by all of this with the negative sign, is going to be equal to what? Minus b. The derivative, I'm sorry, is minus b times the derivative of the logarithm, which is going to have a minus p over q, so we're going to have plus p divided by q, and everything divided by what is inside. So we're going to have w minus px divided by q that shows up here. So this is going to cancel out, and we're going to have this term, which is basically the marginal cost. Now, that marginal cost function can be also plotted here, and it's going to start when x equals 0. It's going to have a value of bp divided by w, and then it's going to increase, and as you can see from this expression, as x approaches w divided by p, it goes also to infinity asymptotically. Now, these two asymptotic properties are very useful because they guarantee necessarily an interior solution. There is an x star given by the intersection of those two curves that fall strictly within the upper and the lower boundaries of the problem. Now, the second step is to characterize the solution, and we can take advantage of the fact that we know that the solution is interior. So we know it's going to be given by the following equations: u prima divided by b prima equal p over q, and px star plus qy star is equal to w. let me emphasize that we can use these equations because of the first step, because now we know that the solution is interior. Now, we know from this objective function that u prime divided by b prime is basically equal to alpha, not alpha, a divided over x star, and all of this divided by b divided by y star. So now we have two equations in two unknowns, and if you do a little bit of algebra, you get that x star is equal to w divided by p times a over a plus b, and that y star is equal to w divided by q b over a plus b. That's the solution to the maximization problem characterized by the interior first order conditions.